right, ladies and gentlemen, we're looking at 11.3, perimeter and area of similar figures. We're going to compare perimeters and area of similar figures using perimeters and area of similar figures to solve real-life problems. If two polygons are similar, with lengths corresponding in the ratio of A to B, then the ratio of their corresponding areas is A squared, B squared. Okay, so let's go through these first four. And actually, I think we're going to skip D because D would be really long. So I don't think I'm going to do D today. Okay, so first of all, we've got to find the ratio. The ratio of the perimeter and the ratio of its side lengths are the same. So we're not going to go through, like for A, we don't necessarily know they're right triangles, but if we did, we could do the Pythagorean theorem and then find their perimeter. But we don't have to do all of that because we know their side lengths and their perimeter ratio is the same. So if I'm going to take big over little for this case, because I've got the big first and then the little one, 12 over 6 reduces to 2 over 1. So that's the ratio for the perimeter and for the side lengths. Now for the area, if we look up, our area is, we take our side lengths and we square them. So we don't actually have to find the area of these triangles. We're going to do it for this first one so I can prove to you that it works. But what you would do for the area is you'd take 2 over 1 and you'd square the top and the bottom, and you'd get 4 over 1 would be the ratio for the area. But we're going to actually find the areas of both of these so I can prove to you that it works. So we're going to take 12 times 8 divided by 2 gives us the area of this whole thing is 48. And 6 times 4 divided by 2 gives us the whole area of 12. 48 divided by 12, what does that reduce to? 4 over 1.
So could you just do like squaring?
Yep, I just wanted to prove to you that it worked. Yep. Okay, so let's do the rectangle. The perimeter ratio, remember, is the same as the side. Which one do we want to use? Do we want to use 10 over 6 or 5 over 3? Okay, we can do 10 over 6. What does that reduce to, though? 5 over 3. And then we take 5 over 3 and we do what to it? Square the top and the bottom, so we get 25 ninths. Can I reduce that? No. So that's the ratio for our area. Pretty simple? Yeah. All right. So again, for C, we get 12 over 6, which is 2 over 1. And how do I do the area again? Square it. So I should get 4 over, this is for perimeter, and then for area it would be 4 over 1.
How come like the 10 don't just down lower like to 2? Yeah, 5.
I'm sorry, what?
Like perimeter, you don't like go lower than 2, you just go stack 5. Like factors 10.
Right, because 10 and 6, the only number that goes into both of them evenly is 2. So that's how I got 5 and 3. If I had like 10 over 15, I could divide them by 5, and I would get 2 over 3. But it's what goes into both the top and bottom evenly. Okay? All right, let's move on to example 2. I'm sorry, this is written so funky. Let me see if I can fix this a little bit. Okay. All right. The ratio of the lengths of the corresponding sides of two similar polygons is 3/7. What is the ratio of its area? So if its sides are 3/7, how do we figure out the area again? Square it. So we should have 9 over 49. Can we reduce 9 and 49? No. Okay, the ratio of the areas of two similar triangles is 32 over 24. What's the ratio of its length? So if its area is 32 over 24, how are we going to find the ratio of its length? Square root it. Good. Square root it. Because if the formula, right, is A over B equals A squared over B squared. What we have here is the area, so we have A squared over B squared, so we have to square both sides to get A and B. So I'm going to square root 32 and square root 24. The square root of 32 is 5.66. And the square root of 24 is 4.89. Yep, let's turn it over. All right. We've got a regular hexagon that has an area of 60 square centimeters. We want to find the scale factor of this hexagon, which is similar to a hexagon, with an area of 96 square centimeters. So if we've got 60 over 96, those are both the areas. What does it want me to do, basically? It wants you to find the scale factor, so that means it wants you to reduce. That's all it's asking. So the first thing I see is what number could go in there evenly? 12. 6. Okay, 6 goes into both evenly, yes. So we get 10 over 16. Can I reduce that more? Yeah. What goes into that? Both of those? 2. So we get 5, 8. And that's my scale factor. All scale factor is that ratio, that fraction reduced to the lowest terms. Okay, the ratio of the length of a corresponding side of two similar triangles is 5/12. The smaller triangle has an area of 24. What is the area of the larger one? So 5/12 is the area of the lengths, is the ratio of the lengths. What's the ratio of the areas then? Isn't it 5?
Oh, yeah.
5/12. So what is, if that's the ratio of the lengths, what's the ratio of the area? 25 over 144. Okay, because that's the ratio. Now we set that equal to, we have the area of the smaller triangle. We're trying to find the area of the bigger triangle. So now we cross multiply. 25x equals 24 times 144, which is 3,456. And we divide that by 25. So the bigger triangle's area is 138.24 centimeters. Okay, the next problems, I'm going to move this up, but not all the way so you guys can see this last one. Okay, a train set is designed to be 1/12 its actual size. So if you took a train, divided it by all the dimensions by 12, that's what our toy train would be. But it's not just the train, it's the whole train set. So if we have a billboard for the train that measures 5.45 inches by 3.2 inches, what would the dimensions of the billboard be in real life? So what would we do to all of these dimensions? If we know that the scale factor is 1/12, we would multiply by 12. Yep. So we've got 5.4 times 12 gives us 64.8 by 3.2 times 12 gives us 38.4. We just multiply by 12 because the scale factor is 1/12. Yeah, that's all I did. If it took Joe 6 minutes to paint the billboard for the train set, what is the rough approximation for how long it would take him to paint it in real life? What would we do to it? We times it by 12. So that would be 72 minutes. Okay, so my real life goes down to 1/12, right? So if I took something for real life, I would divide it by 12. But if I'm looking at the set and I want to know how big it was, I got to go the opposite direction, right? So I got to multiply by 12. Does that make sense? Okay. Oops. All right, the real-life train that Joe modeled his train set crosses a circular pond with a radius of 20.5 feet. How big of a circle should Joe draw to represent the pond in his model train set if he is to stay consistent with the 1/12 ratio? So if the real-life pond has a radius of 20.5 feet, how big should the radius be of the model one? You would divide this by 12. Good. So if we're going from real life to the train set, we divide. If we're going from the train set to real life, we do what? Multiply. So it should be 1.71 ratio is what the train set should be. Questions? Okay, let's get out our handy dandy notebooks.